For the longest time, the playbook for developing large language models was frustratingly simple.
Right.
If your model struggled with a challenging task, complex math, debugging code, that sort of thing, the default solution was always just scale.
Just make it bigger.
Exactly. More parameters, more GPUs, higher costs, and hopefully you'd eventually get the intelligence you needed.
That whole approach was so costly because it made this fundamental assumption that compute was only really useful during that initial massive training phase.
Right.
But this technical report on the Falcon H1R 7B model, it presents a smarter, I think a more practical thesis. They argue a smaller model can absolutely punch above its weight class if it's designed to do two things really well.
Okay.
First, it has to be trained explicitly on high-quality, long-form reasoning traces. And second, and this is key, we have to make inference time thinking harder, cheaper, especially when you run multiple solution attempts in parallel.
That's a fundamental shift in the economics of it. So our mission here is to explore this source material, this technical report on a 7 billion parameter reasoning model to see if it delivers.
On that promise.
Yeah, on that promise to be fast, token efficient, and highly accurate when you scale up the attempts. This is really for you, the engineer or researcher, who cares about practical, shippable reasoning systems, not just theoretical maximums. Let's start with the basics then. Falcon H1R 7B in, say, 60 seconds. What exactly is this thing?
At its core, it's a compact, a decoder-only model, 7 billion parameters.
So pretty small by today's standards.
Right. But it's not just a vanilla 7B. It was specifically tuned for long-form reasoning and then critically refined using reinforcement learning. That RL stage was instrumental because it didn't just chase correctness, it focused on controlling the output length and structure.
And the practical importance of controlling the length, of not having the model just ramble on, that's huge when you think about deployment. So why is efficiency the central feature here?
Because of how real-world agentic systems actually work. I mean, nobody builds a product today that relies on one single perfect output from a model.
No, of course not.
The modern reasoning stack involves what's called test time scaling, or TTS. You sample many chains of thought in parallel, you prune the weak or low confidence ones early, and then you aggregate the results. This 7B model is explicitly engineered to be the low-cost, high-throughput component in that pipeline.
So the hook here is that efficiency under TTS. If I'm an engineer running, say, 64 or even 512 parallel traces to solve a hard math problem, the ability to process that volume quickly, the throughput and the cost per attempt are the metrics that really define success, not just the single-shot accuracy.
Precisely. And the performance snapshot they reported shows strong math, very competitive code skills, and general reasoning that performs well for its size. This means the model clears that bar you need for serious prototyping. You don't have to automatically default to a giant, prohibitively expensive model just to build a reliable reasoning pipeline. This H1R 7B is aimed squarely at making that scalability economically viable.
Okay, let's get into the training, because that's where the magic happens. What specific innovations really differentiate H1R from its base model, the original Falcon H1?
Well, the first key difference is the supervised fine-tuning stage, the SFT. It wasn't just a generic dump of instructions. They meticulously curated data sets with these long, detailed reasoning traces.
Across what kind of subjects?
Across subjects like math, coding, and science. Then they mixed that high-quality reasoning data with, utility domains like chat and tool use to make it well-rounded.
And I noticed a real commitment to long context here. They weren't just proving they could handle it. They actually designed the training around it.
Absolutely. They trained with a default context length of 36,000 tokens, which is already massive.
It's huge.
And then pushed some samples up to 48,000. This is a deliberate, large-scale investment trained on 256 H100s, designed to ensure the model understands and can produce complex, multi-step reasoning without losing coherence.
And after SFT, they moved into reinforcement learning with GRPO. When we look at the specific setup group size 16, temperature 0.85, what really catches my eye are the settings for the KL and entropy terms. They set them to 0. Why would they do that?
That decision is conceptually crucial. I mean, setting the KL and entropy terms to 0 essentially removes certain regularization constraints that would usually keep the model's behavior really close to the policy it learned during SFT.
So they're taking the guardrails off.
Exactly. By removing those constraints, they encourage the model to maximize exploration and roll out diversity. They were training it to aggressively handle long reasoning traces to search widely without collapsing into what we often call rambling, repetitive sludge. They trained it to be robustly creative and long-form.
That successful training leads us right to the benchmarks. And we always have to remind ourselves that benchmarks are, well, they're contracts. They tell you what was measured, how it was scored.
And what failure modes it was optimized to avoid.
Right.
And this report defined its contracts pretty clearly. They organized the evaluation into 3 distinct buckets, which ensures a good breadth of testing. For the math category, they used a serious lineup: AE24, AME25, HMMT25, AMO-Bench, and Math 500.
That's a D field, not just one quick math test.
Correct. The code category had Live Code Bench v6, SciCode, Telecom, and Terminal Bench Hard. And for general reasoning, they used high-stakes tests like GPQA Diamond, MMLU Pro, Humanities Last Exam, and IF Bench.
That's comprehensive.
It is. And I always appreciate when a report details the evaluation settings, like the number of responses per query and the max response lengths, which this one did fully. That level of transparency is essential.
And what about the data contamination check? That's always the first thing that gets scrutinized when high scores get posted.
They addressed it directly. They report 0% exact match contamination for most of the benchmarks and near zero for MMLU Pro. While no contamination check is ever, 100% comprehensive, stating these figures makes the results much easier for engineers to justify relying on.
Okay, let's ground this in the hard numbers from their tables. Where does Falcon H1R 7B really look legit?
The headline math scores are very impressive, especially for a 7B model. AME24 came in at 88.1% and AME25 at 83.1%.
And these are high school to early university level math competition problems. Those are seriously competitive results.
They are.
In code, Live Code Bench v6 was 68.6%. And for general reasoning and knowledge, GPQA Diamond hit 61.3%, with MNLU Pro at 72.1%.
The key takeaway isn't that it's the absolute best model ever released. The implication is that it is not narrowly tuned. It has a strong math bias, for sure, but the code performance is competitive and the general reasoning is acceptable.
So for a system designer, this model meets that critical practical bar of it can handle multiple roles and I can actually ship with it.
That's exactly it.
But every big model launch brings valid skepticism. You need to address the missing data points that make some people use that term benchmaxed. What's missing from this picture?
The first question that gets asked immediately is, where is SWE-bench?
Right.
Live Code Bench v6 is useful for sure for measuring code generation, but SWE-bench has become the industry standard for proving a model can navigate the complexity of real-world software engineering, messy repos, integration tests, file constraints.
All the messy stuff. And the absence of that metric means that specific validation is still on you, the user, to prove.
Exactly. You have to allocate time to validate that competency yourself. The second major question we hear a lot is, show me the post-quantization benchmarks.
Quantization is necessary. It saves VRAM. It allows for higher concurrency and deployment. But can it erode that reasoning edge?
Oh, it absolutely can. The fine-tuned reasoning skills, especially on tasks needing multi-step precision, are sensitive. So if you deploy this quantized, say, using a GGUF format, you have to treat it with engineering skepticism. Meaning you need your own small, focused evaluation set, maybe 20 to 50 of your own representative prompts, just to verify that the performance edge hasn't been lost by that aggressive compression.
And at the end of the day, the production standard remains the same, regardless of a clean contamination report. Does it perform on my workload, under my latency constraints, with my prompts?
This focus on efficiency brings us back to the core differentiator, DeepConf, coupled with test time scaling. Let's make sure we define TTS clearly. It's the explicit strategy of buying higher accuracy by spending more inference compute.
So you just ask the model the same question multiple times?
In essence, yeah. You increase your chances of getting a correct solution.
But the immediate catch is the cost. Parallel sampling burns tokens incredibly fast, and that's what DeepConf is trying to fix. It's an economic solution to a technical problem.
It is. DeepConf is the mechanism that makes TTS economical. It involves generating many solution traces, but then ruthlessly pruning the low-confidence chains early on.
Saving the computational cost of generating a full multi-thousand token failure. So if TTS is the strategy of asking for 500 attempts, DeepConf is the system that says, okay, we've already ruled out 400 of those because their confidence score dropped below our threshold at token 50.
That's the perfect way to look at it. The confidence score, which comes from the model itself, acts as the stopping mechanism. And the setup they described in the report was highly calibrated. They used an aggressive trace budget of K512. They ran a small warm-up of 16 traces just to set a confidence threshold,
Okay.
and then applied that early stopping to the rest. It's truly a process of calibrated ruthlessness to eliminate waste.
And this is why Falcon H1R 7B matters. It improves the curve of that accuracy versus token cost trade-off. It makes that ruthless pruning economically valuable.
The data points here are really compelling. Under the DeepConf at 512 setup, the model achieved outstanding accuracy, 96.7% on both AME-24 and AIM-25.
Wow.
Now, the corresponding token usage is large, around 89 to 95 million tokens, respectively, per benchmark.
Wait, 95 million tokens sounds enormous. Why are we saying that's efficient?
Because that is the total token count needed to achieve 96.7% accuracy across the entire benchmark.
I see, with all 512 sample traces.
With all those traces and all that pruning, the quiet killer feature is that this token usage is demonstrably lower than what a comparison baseline model required to hit that same high accuracy level using the same mechanism.
Got it.
When you're using TTS, the efficiency of your pruning, the cost saved by failing cheaply, is what separates a lab demo from a viable, affordable product. If your agentic system is making dozens of model calls per user interaction, this efficiency is the difference between an affordable service and an impossible cloud bill.
We mentioned the architecture earlier.
Yeah.
Hybrid transformer Mamba style. For the listener who is focused on deployment, how does that architectural choice directly enable this high throughput, low cost parallel processing?
It's a completely practical choice aligned with the needs of TTS. Traditional transformer self-attention, it scales quadratically with sequence length, which is a major performance and memory bottleneck for long context.
It's a huge bottleneck.
Right. But the Mamba component uses a selective state space model that scales linearly.
In-ear scaling is key for long sequences.
Exactly. This hybrid style is optimized for high throughput and low memory consumption when you're dealing with two things at once: long sequence lengths and high batch sizes. That is the definition of a modern reasoning stack.
Long outputs, many parallel traces, and stable throughput under a heavy load.
That's it. And the inference specs in the report back this up. They documented a configuration with a 256K context length and reported vLLM throughput comparisons against competitors like Qwen38B, citing improvements from 20% up to 100% on H100s. This model wasn't just trained for reasoning, it was engineered explicitly for volume.
So for the listener who's ready to evaluate this model, we need some practical guidance.
Yeah.
How do you approach Falcon H1R 7B without immediately getting bogged down in complexity?
Start simple. Fastest path first. Use the hosted demo or a community chat surface. Test it with explain your reasoning prompts, give it challenging multi-step math, and importantly, check if it handles tool-style structured output like JSON or YAML with consistency. Your goal here is to quickly assess its persona and decide if it earns local time.
And if it does earn local time and you're going down the GGUF path for local deployment, what's the structured engineering workflow?
The key is realism. Start with realistic prompt lengths. The practical workflow should be picking 20 to 50 actual prompts you care about, running them at your target context and output lengths, saving the full results, and this is crucial, changing one thing at a time.
Just one.
Just one. Change the quant level, rerun. Change the temperature, rerun. This methodical approach is the only way to learn the model's true performance profile, rather than just relying on high-level charts.
And if you're serious about production, the server path using something like vLLM is non-negotiable, primarily to accurately test batching and measure the latency hit of those parallel traces. Time for a hardware reality check, because this is where the costs hide. We've heard 256K context window, and it sounds like this magical free feature. It is not. It's a massive expense.
It is an immense cost multiplier. The report documents using that 256K context length and aggressive generation lengths up to 64,000 tokens per trace in that DeepConf evaluation. This combination of massive context plus long generation is powerful, but it demands serious VRAM.
The 7B parameter count seems fine, maybe 15 or 16 gigs for the weights. Where does the cost explosion actually come from?
The weights aren't the problem. The KV cache is the memory killer. Every parallel trace and every additional token in the context window consumes VRAM for the key value cache. So long context plus long outputs multiplied by high concurrence, all those parallel traces, it means your memory usage accelerates incredibly fast.
So the grounded guidance is clear. Your hardware needs depend far more on your sequence lengths and the concurrency you need for TTS than on that 7B label. You absolutely must test at the maximum lengths and batch sizes you plan to ship. Let's expand on quantization for a second. It provides VRAM savings and concurrency, but we have to warn you. Reasoning models are the most susceptible to subtle failure here.
The core issue is the inherited uncertainty from the lack of published, full post-quantization tables. You're flying blind. You might save 10 gigabyte beat RAM, but at what cost to reasoning accuracy? I've personally seen multi-step planning agents fail instantly because of an aggressive Q40 setting.
Which is why that verification on your own prompts is so essential.
Precisely. Treat the quantized file, the GGUF, as a deployment convenience, not a truth machine. Pay special attention to tasks that require long, careful reasoning chains, because that is where the small numerical approximations from quantization can snowball into a catastrophic failure.
Finally, we have to turn to license and adoption risk. This is the critical, non-technical part of model selection that can cost you millions if you ignore it.
Since this model is positioned within the Falcon family, due diligence on the Falcon LLM license is non-negotiable. This is the least fun part of evaluation.
The least fun.
But skipping it can be the most damaging.
So for someone evaluating this for a commercial product, what's on that essential checklist beyond simply, is commercial use allowed?
You need to check the fine print on redistribution rules. Can you embed this model in a proprietary product? You have to read the acceptable use policies, which can restrict certain applications. And crucially, look for any downstream restrictions that might affect how your customers or partners can use your product.
Right.
Remember, a technical license violation can undo all the performance gains you worked so hard to achieve.
So let's summarize the report's findings for you. If you are deeply involved in math-heavy workflows, or if you're building an agentic system that's architected specifically to afford multiple parallel attempts, Falcon H1R 7B is a serious practical candidate that really demands a spot in your evaluation queue.
The core insight of this model is that combination of highly targeted training with efficiency under test time scaling. It's not an academic curiosity. It should be treated as a measurement decision tested rigorously against your specific workloads, not a fandom decision.
Here's a thought to carry forward and explore on your own. Falcon H1R 7B is compelling because it fundamentally changes the cost calculation of intelligence. It makes more thinking, that is, running hundreds of parallel traces, feel less like an unattainable luxury feature and more like something you can actually budget for and build around. So if the cost of high-quality reasoning just dropped dramatically, how might that efficiency allow you to radically change the architecture of the agentic system you are trying to build?